Hi, my name is Ibrahim Kashkoush from the University of Haifa, and I will present our work on cpuC, a dynamic reconfigurable architecture for accelerating convolutional neural network. I will show how cpuC achieves single-cycle convolution at very low power, making it especially suitable for embedded and edge AI system. Convolutional neural networks are everywhere today, in cameras, autonomous systems, mobile devices, and IoT. Most acceleration relies on GPU, which offer great performance, but at a power level that is not practical for many embedded or edge platforms. On the other side, CPU are flexible but do not provide enough parallelism for convolution-heavy workload. Our goal is to bridge this gap to design an architecture that can execute CNN workload with GPU-like throughput but at a fraction of the power and the area, suitable for embedded systems.
Our starting point is the CGRA model, where we have an array of ALU and reconfigurable interconnects that allow us to shape the data path to a given computation graph. However, existing CGRAs often use a fixed 2D mesh, and the restricted connectivity make it hard to fully utilize all functional units and memory modules. This leads to underutilization and complex compilation. cpuC take a different approach, using a fully reconfigurable crossbar to avoid this connectivity limitation.
cpuC is a cross-grain reconfigurable architecture that uses a dynamic crossbar instead of constrained 2D mesh. At each clock cycle, the crossbar physically connects registers, arithmetic units, and memory ports to form a custom circuit that directly implements a multi-operation instruction. For CNNs, this means we can configure cpuC so that an entire K by K convolution is computed in a single cycle, exploiting massive parallelism while keeping the design very simple. At the instruction level, cpuC uses a crossbar to connect sources and destinations, enabling an entire data flow subgraph to execute within a single cycle. For example, one instruction may multiply R1 by the sum of R3 and R4, while simultaneously updating the program counter based on the comparison between our memory outputs. The instruction configures the tri-state signals, such as the red arrows in the example, to perform the operation R1 equal to R1 multiply to the sum of R3 and R4. Non-updated register automatically preserved so that a single instruction corresponded to a fairly large directed acyclic graph that executed in one clock cycle. For example, R0 is not updated in this instruction, so in the instruction it will be R0 equal to R0. cpuC is highly configurable. In the very long description, we can define the word width, the number of arithmetic units, boxes, and the number of registers and memory modules. The PC itself is treated as a regular register and can be updated via MUX operations, which allow flexible branching, including dynamic loop control. Each instruction can update many registers and memory ports in parallel, and can have a compiler assign latency to match the depth of the data path we create. If we try to fully parallelize a 6x6 convolution, we will need 36 parallel memory reads, 36 multipliers, and a large ALA tree, which is not realistic for a small embedded architecture. Instead, we introduce what we call pipeline convolution. We maintain the sum of the columns as 0 to as 5 And when we shift the convolution window by one position, we compute the new output as new. And the new output is the previous convolution output minus S0 plus the new as new. This reformulation requires only 6 parallel loads, 6 multipliers, and a much smaller adder tree, which fit nicely in cpuC resources. To support pipeline convolution efficiently, we also need an appropriate memory system. We implement a hexaram module, which is logically a 6-port memory built from 3 BRAM blocks. This design allows us to perform 6 parallel loads and up to 2 stores in the same cycle. This is exactly what we need for fetching the 6 pixel and 6 weight that feed the pipeline convolution at each step. To verify that pipeline convolution is still usable in practice, we applied it to 3 Cyan convolution neural networks: YOLO V7, FastR Cyan with ResNet 15, and LitNet. In all these cases, when we replaced regular convolution with pipeline convolution only at interface time, the network deducts essentially the same object. Differences mainly occurred on a small or blurry object. We believe that if both training and interface were done using pipeline convolution, even these differences would be minimized. We compared the convolution kernel running on a standard Intel i5 processor using optimized C code against our cpuC implementation. The CPU requires about 45 instructions and 33 cycles per iteration, while cpuC executes the same logical work in a single instruction and a single cycle. Assuming similar delay per operation, this translates to roughly a 10 times speed up compared to the CPU for the optimized version, and around 36 times faster than the straightforward convolution loop. Synthesis results show that cpuC consumes about 0.15 watt with modest use of LUT block RAMs and DSP blocks, making it very suitable for embedded or edge deployment. There is a rich body of work on CGRAs, such as MT-CGRA, HeartMap, FPCA, LISER, and EGRA. Many of these architectures rely on mesh or column-structured connectivity and require a complex mapping or binary translation technique to achieve a good utilization. cpuC distinguishes itself by using a fully reconfigurable crossbar and aiming explicitly at single cycle execution of a large multi-operation instruction. Combined with our pipeline convolution, this makes cpuC practically well suited to the CNN workloads. To conclude, cpuC is a cross-grain reconfigurable architecture that uses a fully dynamic crossbar to execute a large multi-operation instruction. With our pipeline convolution transformation, cpuC can perform convolution with very high parallelism, achieving significant speed up compared to a general purpose CPU, while consuming only around 0.15 watt. Future work include training network directly with pipeline convolution, extending cpuC to additional layer types, and exploring scaled ASIC implementations. Thank you for listening. I will be happy to take any questions.